And this is 4-2 beta lesson, okay? And here's a question from the end, right? This is a different question on the alpha lesson, and it says this. All of the following satisfy the conditions of the mean value theorem on this interval, -1 to 1, except for one of these. We talked about this. The mean value theorem says, if a function is continuous and differentiable on an interval, then at some point during the interval, the instantaneous change, the slope of the tangent line, has to equal the average change, the slope of the secant line. And all this stuff, you know, you sit here and you like listen. I don't know how well you process what that's about. And you need to be aware that the YouTube page is up to date. So if we said something, me saying it doesn't mean you process it. If you need to go back to the YouTube page, you don't have to watch the whole video. You can say, yeah, something happened at the beginning and I was kind of like zoning out. I don't really remember what he said. Just watch the first 3 minutes. So, the conditions are that it is continuous and differentiable. So on this interval, one of these fails at least one of the conditions. So without answering the question, we'll just go to E. Ready? What's the problem with choice E? X divided by x take away 2. When? Or 2. See, if you put 2 in here, 2 makes the denominator 0. So you'd have 2 divided by 0. No value for 2 divided by 0, it would be discontinuous. William's correct. But that's not the answer. Why not? Because the interval is -1 to 1. So that has a problem if the interval was -2 to 2 inclusive. But in that interval, you're fine. So it's one of the other choices we'll come back to. This is the same thing from the alpha lesson. It's the H chart. The sooner you get on board, organize your information in the H chart, the more successful you'll be. Okay, so this is set. In the book, they call these points A and B. So I'm going to rebel and call them X of 1 and X of 2, because it makes no sense to me that C is between A and B. This is your T-chart. We expand the T-chart with a column to the right, make it an H-chart, which is the value of the derivative, the instantaneous change. And at this value, which is somewhere in between here, the derivative equals the average change. This take away this over this take away that. Right. And we talked about this during the alpha lesson, but you already know it, except that's a justification for why when the parent graph is increasing, the derivative is positive. When the parent graph is decreasing, the derivative is negative. You don't need to write this down. You already are aware of this. That's a justification. So we're going to go to example 6. We're on page 199. So you have this. Where is the function? X cubed take away 4x increasing, and where is it decreasing? Oh, there's a picture right in the margin. Yeah, this is a non-calculator problem. So we're drawing the picture to help you see what's going on. Give the expected inputs the layup, even though it's without a calculator, if you understand conceptually what's going on. So So we're going to differentiate this. Here's the parent graph. It's a cubic. Here's the derivative. It's quadratic. In second degree, it has 2 zeros. How many are real? 2 or none. In this case, it's 2 real zeros. You would get 3x squared plus a negative 4 equals 0. Add 4 to both sides. Divide both sides by 3. X squared equals 4/3. Get the square root of both sides, and you would get the positive and negative root of root 4/3, which is a number a little to the left of negative 1, a little to the right of positive 1. Logical? So we take a number line, or in this case, we have our table. So I built this table, the H chart. These are the critical points. Negative root 4/3 from here makes the derivative 0. Positive root 4/3 makes the derivative 0. So we pick points to the left of those points and to the right of them. So the easiest way to start is 0. You put 0 in the derivative, cover-up method, you get a negative. Make sense? You got a negative when you put 0 in the derivative, so the parent graph necessarily was falling. Then I go up here, put negative 2, which is to the left of negative root 4/3. Negative 2 squared is 4. 4 times 3 is 12. Take away 4 is positive. Parent graph's increasing. 2 is going to be positive. Parent graph's increasing. Well, how do I know it doesn't change direction somewhere else? Because I don't have the picture. You know because of the fundamental theorem of algebra. The derivative is a quadratic. It only has 2 zeros. Then what? If you have a local max or local min, then you have a critical point where the derivative is 0 or fails to exist. If you have a critical point, that doesn't guarantee you have a max or min until you verify the sign change. But you don't need to have the picture of the graph, because they're the only 2 times the derivative is going to be 0. So interval notation, the parent graph is going up until you get from the left, until you get the negative root 4/3 and positive root 4/3 to the right. And in between, it's decreasing. The bracket notation means this. It means the function's continuous. It does not mean the graph is simultaneously increasing and decreasing at those critical points. Okay? That's it. You organize the information, you build the H chart, and you make a conclusion based on the H chart. So we're going to pause the video. We're going to leave that up there. That's your model, and you're going to go to problem 27. It would look like this. Here's the derivative. What do we do? This is what the derivative looks like. So I use the calculator for that much. Second trace 0. You learn how to do second trace 0. You have to surround it with the left and right band. So when you do that, see what happens to the screen? It tells you x equals this value right down here. Second quick. Paste X on the home screen, and I stored it. Store in alpha L. Why? Because that's the left point, the left 0. Doesn't matter what letters you pick. But once you move the cursor, you're going to lose that value. The right 0 is here. So your table looks like this. Your H chart, here are the two zeros. These values make the derivative 0. I went to the left of that, in between to the right of it. There's a sign change there. You can see from the picture the derivative. The derivative over here to the left of that 0, the derivative's above the x-axis, so the parent graph is going up. In between these two, the derivative's negative. The parent graph's going down. To the right of that 0, the derivative's positive. The parent graph's going up. The intervals would be, here's where it's going up, in between is where it's going down. Okay? What I did here is I put those values already stored into the function to see what the height of the graph was, the parent graph, at that time. Seems like a lot of clutter on the screen, but they weren't asking for these values, but that's the point of storing them. So you're not going to have a rounding error because the calculator is bringing that entire value to the home screen. Example 7. So we're on page 200. Find the function whose derivative is sine x and whose graph passes through the point 0, 2. Think about this. This is a hint at what you're going to do in the second part of the course. You do differentiation, and then we'll get to anti-differentiation, which this is. It's like Jeopardy. They're telling you the answer. Okay? It says the derivative sine x. So if the derivative is sine, what was the question? What was the parent graph? We saw over there. The derivative of cosine is negative sine. So the parent graph must be negative cosine x. Logical? These aren't difficult differentiations. So the parent graph for problem, for example 7, is negative cosine x. It would look like this. Here's the point. F of 0 equals a negative 1. The opposite of the cosine graph. And they're telling you that in the parent graph they're looking for, it goes to the point 0, 2. No big deal. We just have to move the graph up 3. To move it up 3, we slide it 0 right or left up 3 by doing the opposite to y. Y take away 3 equals negative cosine x. Done. They gave you the answer they wanted the question. The answer is the derivative is sine x. The question is the parent graph is y equals negative cosine x plus something. Might be plus 0. But if you add anything to that, when you differentiate, you get a 0. So all these graphs would be stacked. All these negative cosine graphs would be stacked in here. Because they all have the same shape. They all have the same derivative, which would be sine x. They're stacked like what? Like Pringles. You know what Pringles are? They're this, I'm not sure what they are. They're this food stuff. But what I'm interested in is the packaging. It doesn't matter where the Pringle sits in the can, it has the same shape. And that's what the derivative is about. It's about the curve. Not in the last 40 years. I don't think they're really helpful. But the point is the shape of the can. Like the Pringles are all stacked in there, just like these negative cosine waves are all stacked. They have the same shape. And we needed some other information about some point the parent graph went through. And that point was given to be 0, 2. So we moved the whole graph up 3. Okay? So that's your model. Now you got to listen to this. You're going to go to 35. Okay, so what do we have? They tell you for this problem, 35, the derivative is negative x to the negative second, which means what? The derivative is negative 1 over x squared. That's the derivative. What the parent graph had to be. So I'm going to undo that. What happened? I undo replacing n with n, take away 1 by adding 1 to that exponent. Negative 2 plus 1 would be a negative 1. The parent graph would have a degree higher than the derivative. Then instead of multiplying by this, you divide by that value. The negatives reduce. What do you get? You get x to the negative 1. 1 over x. Let's see if that works. If I have x to the negative 1, the derivative would be negative x to the negative second. Which is that? Then what? They wanted to go through the point for 2, 1. Okay, so I put a 2 in here. If you put a 2 in the parent graph, you get 1/2. So it goes to the point 2, 1/2. You want it to go to the point 2, 1. You slide it up 1/2. So the magnitude of the slide is 0 right or left, up 1/2, which is just this. Well, I take away 1/2 equals 1 over x. So, if you are at home, you are dismissed. You go to the exit ticket. We will see you in the building tomorrow. If you're here, then we're going to go over the problem in the PDF.